All right. So hello, everyone. Thanks for coming to today's lecture. At the beginning, I'm going to talk a little bit about the quiz 2. So if you have any questions, just unmute yourself and then ask me. All right. All right. So quiz 2 will take at the beginning of the lecture in next week. So it will be similar to what you have for quiz 1. So which means at the very beginning, we will start the quiz 2. You can download the quiz 2 question paper, and then, or you can view it online, that's totally fine. Then you need to put the answer, write the answer down onto a document, Word document, that's fine. Or you can simply handwritten the answers onto the paper, onto your paper, and then take a picture. All right, and when time's up, submit your questions to me. Submit your questions on the UTS online. All right, so that is the way to perform quiz 2 is like similar to quiz 1. You download the question paper, and then you can write the answers in a Word document, or you can handwritten the answers on the paper and take picture. All right, and after time's up, upload your question on the UTS online. All right, so that is the way we take the quiz 2. And for quiz 2, it is quiz 2 it is 15%. It is 15%. And then it will be 2 or 3 questions. It will be short or long answers or calculations. All right. So there will be 0 computer activities. All right. So like in quiz 1, you have the calibration, but now we don't have any computer activities, but you can use the computer to calculate something. That's the thing, because in this semester, we can't do the restrict open book. Previously, we did it as a restrict open book, and then to let you to have an 1-page handwriting double-sided A4 paper. And that is a practice for the final exam. That is a practice for final exam, because in final exam, in the previous final exam, then you will have, it's a restrict open book as well. Then you have 2 double-sided A4 papers handwritten. Then you can take in. But in this semester, because we can't take proper exam anymore, and for this quiz 2, we can't take it in the real class. So the restrict open book is released. It's removed. So which means you don't have to think about the restrict open book. You can do an open book, and you can do some calculation by using MATLAB or something. So they're totally fine. So it's totally up to you. Just to write the answer and send it back, upload it back to the UTS online. All right. So it will be 15%. It will be 40 minutes. You will, at the beginning, you will have 5 minutes to download the the question page, and also to read the questions. All right. So don't be late. Don't be late next in the next lecture. All right. So the first 5 minutes, you will need to download the question paper, and also read on the questions. And then after the first 5 minutes, you will have 40 minutes to finish the quiz 2. You will have 40 minutes to finish the quiz 2. And after that, you can upload the Word document if you want to write it in a Word document, or you can submit the picture, which is taken from what you wrote on the paper, and to submit them to the UTS online. All right, so there will be 2 or 3 questions, but in each of the questions, there will be sub-questions as well. and they will be definitely include the calculations. All right, but the good thing is you do need to think too much about the if you can calculate by hand or not, because it's not restrict open book anymore. So you can use MATLAB to do any calculation, but you need to write down the solving process. All right, so you need to write down the necessary equation and the ideas and the process you want to solve the question, and also the final answer. It's not a final answer only. All right. So any questions about quiz 2? It's just unmute yourself and ask, please.
If we just give a screenshot of our MATLAB script, is that enough? Is that enough evidence that you know like what you're doing?
I don't want you to do that. You can do a MATLAB calculation, but it's better if you can handwrite or you can write your equation yourself.
All right, thanks.
No worries. Any other questions?
So we get marks for the working out as well, right?
Yes. So if you write your process about solving, or you write the right equation, then you will definitely get a mark if your final answer is wrong. So what I mean is, suppose I'm asking you to do a projection, like similar to what you have in quiz 1. Then if your final answer is wrong, if a final projection value is wrong, but you write the right equation about how to calculate it, it's just about the calculation, then I will definitely give you marks. Or another example is, for example, if I'm asking you to assess the stability of the linear continuous time system. All right. So there are several steps. First step is get A. You answer the stability of the system only depends on A, and you can also answer the criteria. Right. For example, if all the eigenvalues are are negative or have negative real parts, then that is stable. Right. So you write down that. And then the next step is you will calculate the eigenvalues, right? And your process is 100% correct, but just about calculation, your eigenvalues are wrong. And then the wrong eigenvalue results in a wrong conclusion about the stability, but I can still give you half of the mark, something like that. So I do suggest write all the necessary process in solving the problem as detailed as possible. Then I get some points, and then I can give you marks, even your final answer is wrong. All right, but the thing is, if you, for example, about stability, if you write the criteria about stability which is not correct, I will not give too much of your marks, but I will give other marks if your eigenvalues are correct, something like that. All right, so it's some kind of like you write your details of your answers, and then if some parts are correct, I'll definitely give you the marks. Yeah, any other questions? Okay, so the topics, I can't say.
Could you repeat which topics we're covering in quiz 2?
Yeah, sure. I saw the chat. So I can't say it in that quite details about the topic, but it will cover everything after quiz 1 and until today, until what we have today. So it's like after quiz 1 and until what we have today, including what we have today.
Okay, thank you.
No worries. So any other questions about quiz 2? Any other questions from about quiz 2? All right. So if there's no questions, I'm going to today's lecture. But feel free to post your questions in the chat, and then after the lecture, I will have a look and then I will answer the questions. All right. Cool. So let's go to today's lecture. Wait a minute. Yep. So as I mentioned, there will be 3 lectures about control part, and the first lecture is what we had in last week, which is about the linear continuous time system. And then in today's lecture, we will have linear discrete time system. It's still linear, but the system is not continuous. It's discrete. It's discrete. And then in the last lecture of the control, which is the lecture after today, then we will introduce the nonlinear discrete time system, which will be much more closer to the real case. All right. Then in last lecture, we mainly introduced the linear continuous time system, and then we first introduced the standard formulation of the linear continuous time system, and we used some real cases to formulate the system to the linear continuous time system. For example, the jacking system, or it's similar to the cruise system, or it's a damping, it's mass damping spring system. Then we formulated as well. I think in the tutorial you are formulating a bit more cases about the linear continuous time system. And then after that, we introduced the stability of the system. The stability of the system. The stability of the system is about if the state will converge to 0 if the time increases. All right, so that's the stability. And then we introduce how to check the stability, how to assess the stability. Then that is the stability only depends on the matrix A. So if you remember, there will be A, B, C, and D 4 matrices in the standard formulation. And the stability only depends on the matrix A. And the criteria about stability is if all the eigenvalues of the matrix A are negative or have negative real parts, then the system is stable. So remember that, because the stability criteria for the linear continuous time system is different from the linear discrete time system, which is what we'll have today, right? So that is different. So try to distinguish them. All right. So after you check the stability, if your system is not stable, but you want to make your system stable, then what you can do is we use a state feedback control. We call it as a feedback control, but that feedback is your state. Suppose you can use some sensor to observe your state, then you use a state feedback control. Then after you use the state feedback control, you make your control U is equal to minus kx. Then your new A matrix for the state feedback control is A minus bk. A minus bk. Right? Then you can choose proper k to make your new system A minus bk stable. Right? So that is the pole placement. The pole placement is you first use the state feedback control. Use the state feedback control. Then you change your system from AX plus BU to A minus BKX. Right? And you can choose proper K to make A minus BK has all the eigenvalues negative. Then the new system is stable. Right? But the thing is, not all the systems you can do this kind of pole placement. Then before doing pole placement, you need to check the controllability. So that's another idea introduced, controllability. So for the controllability, it's quite easy. You just formulate the controllability matrix. If you remember, it's an infinite matrix, but you can make it as a square. It's B, A, B, A times B, then A squared times B, something like that. All right. So if the criteria is about state controllability is if the controllability matrix has full rank, then it is controllable. All right. And how to check it is full rank, I introduced two methods. One is the mathematical method. Then you just need to calculate the determinant of the controllability matrix. If the determinant of that matrix is not equal to 0, then it is full rank, which means it is controllable. Right. So that is the okay. So I think you've got nearly everything about some of you may nearly forget everything about what we talked about in last lecture. It's just a review about the linear continuous time system. Yeah, where we talk about. There we go. That's the controllability. Here's controllability, right? So if you check the controllability, you need to formulate this controllability matrix and to check if it's full rank or not. And there are two ways to check the to check if it's full rank or not. One way is you calculate the determinant of this matrix. All right, so I've said it already. And another way is, more intuitive way is, if you can use one row or one column of the matrix to present the others. Right, for example, in this case, so if you time -2 on the first column, then you can have the second one. Then which means that is not full rank, which is not controllable. All right. Then after that, we introduce the linear quadratic optimum control, or just call it optimum control. Why we introduce that is, when you do the pole placement, you can have multiple choices of K to make it. You can have multiple choices of K if you do the pole placement to make the state feedback control system stable. Right? But which one is the best? Which one is optimal? Then that is the optimal control. The aim of the optimal control is to find a K to make this performance index minimized. That is the objective of the optimal control. And how to do that is, you do need to know how to solve the Riccati equation. So the first step is you solve the P from the Riccati equation. So from the Riccati equation, all the metrics are null except P. Then you solve the P from the Riccati equation. Then the second step is you substitute P into here to calculate K. Then after you have P, you can calculate K. And after you have K, you can calculate U. You can calculate U. And you can also calculate the minimal performance index. So that's the linear quadratic optimal control. All right. So this is what we have in last lecture, and then let's go into today's one. So today we are mainly talking about the linear discrete time system. So which means the system is still linear. It's still linear, but it is discrete time. It is discrete. It is not continuous. So first, we will introduce the linear discrete time system, the standard formulation, and also some examples about how to formulate the control system from the real case. All right, and the linear discrete time system, I will introduce a little bit later. It can be transformed from a linear continuous time system. Then the technique we used to do that transformation is discretization. So which means we can use discretization to transform a linear continuous time system into a linear discrete time system. And there are two methods in it. And after that one, we will have nearly the same thing as what we have in the linear continuous time system. One is the stability. So for the linear discrete time system, we still have the controllability issues, if this stability issues, if it's still stable or not. And also we will have the controllability issue and the state feedback control and the pole placement. We will have nearly similar things on that. And also if we want to choose the optimal K, then we will have optimal control as well. So after the discretization, the stability, controllability, and pole placement, and optimal control, we have everything introduced in the linear continuous time system. So I think most of you will know what they are doing, right? Why we use that, and to do it for what, right? But the thing is, some techniques in here is a bit different. For example, the stability criteria is different comparing to the linear continuous time system. And also for this for the pole placement, because the stability criteria are different, then how you choose K is a bit different as well. And also for the optimal control, the main idea is exactly the same, but equations are slightly different, and you need to distinguish them. All right, then in the hands-on activities, then we will have some examples. Then you can work with, and also you can solve problems by using the MATLAB. Right. So let's go to the introduction about linear discrete time system. So for the discrete time models, describes the relations between sampled variables. So which means it's not continuous, it's sampled. It's sampled. As you can see, the x, u, and y inside that, the variables are k, ts. The ts is the time interval. The k is the sample. Right? So if it's not continuous anymore, is about the relationship between the sampled variables. All right, they are sampled variables. That's the first difference. And the second point is the value of the state xkt keep constant during the sampling interval. So which means if you can see the figure here, so if it is continuous, the state will change at any time. But in the discrete time system, within the interval, the value of the state keep constant. It keeps constant here, it keeps constant there, it keeps constant there, it keeps constant here. So that is another property of the discrete time system. And the third property of the discrete time system is a discrete time system can either be naturally discrete, or it can be converted or sampled from a continuous time system. Right? For example, on the right hand, on the bottom right figure, you can see this system is naturally discrete, right? But on the bottom left figure, you can see if naturally it is a continuous time system, we still can do some sampling to convert or transform the discrete time system, the continuous time system to a discrete time system. This is what we are going to introduce about discretization later. All right, so there are three properties in the which are different from the continuous time system. Right? Then let's first start considering a very, very simple first order linear continuous time system. If you remember in the discrete time system, in the continuous time system, here, so the difference equation is about the derivative of the state with respect to time is equal to a linear function of the state and also the control, right? So it is about a relationship between the derivative of the state with respect to the state and also the control. All right, but here, for a very simple one-dimensional case, here is a bit different. So why is different? Because it is not continuous time anymore. Then we can't calculate the derivative. There's no derivative because it's not continuous, right? And here, the difference equation is the state in the next time step is a linear equation. It's a linear equation of the current state, and also a linear equation of the input or the control. But here, for a very simple case, I didn't mention that. So it is a bit different because there is no x dot there. Instead, it is xk plus 1. So xk plus 1 is a linear equation of xk, which means the next state, the state in the next step, is a linear function or linear equation of the state in the current time step. All right, so that's still the difference equation, but it is a little bit different from what we have in the continuous time system. So in this case, it's quite easy to get the solution, but this solution is only for this simple case. So for this case, because the current state times A is equal to the next state, so then the solution is xk will be equal to A power k times x0, right? And in this case, if A is equal to 1, and the solution, the state will keep constant, right? So if A is larger than 1, then the state will come to this way, the blue stars, right? And if A is between 0 and 1, then the state will change as what we have in the red. All right, so that is a very simple case about the linear discrete time system. Then let me give you an example to formulate the linear discrete time system from the real case. The example is about the wealth of the bank account. So suppose K is the year counter, and that is definitely discrete, right? So that is year counter. It's year 2020, year 2021, something like that. That is different. That is definitely discrete, right? And rho is the interest rate. And if we consider xk is the wealth of the bank account at the beginning of year k, the xk which is the state, is the wealth at in the bank account at the beginning of year K. And UK is the money saved at the end of the year. At the end of the year. So which means in the year 2020, which is K, then my account, at the beginning, my account has about XK money. Then at the end of the year, I saved about a UK money into the account totally. All right. And the X0 is the initial wealth of the bank account, which is the initial state. All right. Then in this case, if we want to formulate it into a linear discrete time system, what we need to think about? So in the linear continuous time system, as I mentioned before, so you need to first formulate the physical equation, right? I think for both of the cases we use the Newton's second law, right? But here it's a bit different. We need to start from what's the relationship between xk plus 1 and xk. After you have that relationship, then you can formulate the system. All right, because in the system it describes the state in the next time step is a linear function of the current state and the current input. Right? So if we can what happened? Okay, oh good. Right. So if you can get a formulation about the state in the current time step and the state for the next step, then you get the formulation. So which means if you can have a formulation which can only have xk plus 1 and xk and also uk, then you formulate the linear discrete time system. All right, so let's go back to this example and let's formulate it together. And after that, you will have some activities about formulating it by yourself. All right, so from the example, we can see the xk is the wealth in the account at the beginning of the year K. So we want to find what is xk plus 1. What is xk plus 1? So xk plus 1 is the wealth at the beginning of year K plus 1, right? So I think it has 3 parts. The first part is the wealth at the beginning of year K, right, of last year, so which is xk. And another part is the saving in the total year K, which is uk. And the third part is the interest, which is rho times xk, right? And then we have the relationship between xk plus 1 and xk, right? And then that's the formulation of our linear discrete time system for that example, right? So the money in my account in next year, there are 3 parts. The first part is the one in the last year. Suppose I didn't spend anything. And the second part is what I saved in last year, right? And the third part is the interest I got, which is rho times xk. And then after you have that, then you formulate the linear discrete time system. And here's an example. So suppose the initial state, the initial wealth in my bank account is 10K. Then if every year I save 5K in it, and the interest rate is 10%, it's not that high, but I mean, suppose it's 10%, then you can put those numbers back into your linear discrete time system. Then we can get the solutions. Seems like can't. Is he in? Yeah, it's interesting. Okay, so then on the bottom right figure, that is the solution or the change of the state of my bank account. You can see in each year it's constant, and then every year it's changed. So that's a discrete time system. All right, so at the beginning, I give a very simple case about only one dimension of the linear discrete time system. But the linear discrete time system, as I mentioned in the continuous time system, it can handle multiple variables in the state. So in this case, suppose you have n states. Then for each of the state, you can write a difference equation. So which means xk plus 1 is a function of x1k to xnk. X2k plus 1 is also a function of all the states. Xnk plus 1 is also a function of all the states. Then that is n first order linear difference equation for the linear discrete time system. And then we can rewrite it into a compact matrix format, which is xk plus 1 is equal to axk plus buk. And that is the standard formulation of the linear discrete time system. And the x can be multiple directions. It can multiple dimensions, so it can be multiple variables in the state x. All right, so let's compare the linear continuous time system to the linear discrete time system. So what are the differences? All right, so the first difference is it is xk plus 1 instead of x dot. That's the first difference. If you find x dot, then that means it is continuous. It is continuous time system. Because if it's not continuous, you can't calculate the derivative. There's no derivative. All right. So that's the first difference. The second difference is it uses t in continuous time system, but it uses k and k plus 1 in the discrete time system. Then which means it uses time, which is continuous in continuous time system. But it uses the time step k instead of time in the discrete time system. All right, and another difference is in a discrete time system, it has xk plus 1. And then in the continuous time system, that is the x dot, which is the derivative of x with respect to t. All right, so there are several differences. Between the discrete time system and the continuous time system. So if I give you a question in the final exam or in the quiz 2, the first thing is you need to check if it is continuous time system or discrete time system. If I give you a real case, right? So if it's continuous time system, you use the methods, you use the criteria in the continuous time system. If it is discrete time system, you use the methods, you use the criteria for the discrete time system. This is quite important because in every semester, I have the questions. I have the problems that students will miss the discrete time or continuous time system, and then they will make a wrong answer to the questions. All right. So the first thing is you need to identify if this is discrete time system or continuous time system. Then you can get the right answer. All right. So that is the comparison of that. And if you remember, for the continuous time system, the solution is something like what we have on the slide. Right? And if you remember, what's the meaning of the solution? The meaning of the solution is if you have a starting state xt0 or x0, then you can calculate the x state. You can calculate the state x at any time from the solution, right? So if you look at the solution, and if you have t and x0, then you can calculate the xt, right? So that is the solution. But comparing to the solution in the linear continuous time system, in the linear discrete time system, it is a bit different. So the solution is the equation on the bottom. That is the solution for the discrete time system, linear discrete time system. And it is different from what is it for the linear continuous time system. So that's why I mentioned, first you need to identify if the system is continuous time system or discrete time system. And then after that, if I'm asking what's the solution, then you get a right answer, right? So in the solution, there are two parts. The first term in the solution, we call it the natural response. Then which means without any input, the response will be like that. The state will change like that. All right. The second term, we call it forced response. Then which means this response mainly depends on the input, or why we call it forced response, right? Because it mainly depends on the input u. So this is the solution. And again, the meaning of the solution is if you have an initial state x0, you can calculate the state at any time step. That is the solution. All right, and if you have a question in your final exam or in your quiz 2, I'm asking you to write the solution. You just need to put the actual A into there, and actual B into here. And that's all. You don't have to do the calculation inside. Suppose A and B are matrices. All right, so you just write down this equation and replace A and B from the real one. And that's it. You don't have to calculate inside. All right, then that's the solution. Then here I gave an example. About this solution. And suppose we have two first order difference equations, and we have two variables, which is x1 and x2, and we have this kind of first order equations. Then we can rewrite it into the matrix format, which is something on the top right. And then if we calculate the solution, and again, if you have a question about calculate the solution, you just need to write it something like the first equation. You don't have to do the calculations after. You just write it there, and that's totally fine, because sometimes it's quite hard to do the calculation inside the matrix if you have a power on it. All right. So, but in this case, because we have a special matrix A and B, then we can calculate inside. Then we can get this solution like that, and we can plot the change of the state at different time steps like that. All right. So suppose we gave a constant. Input as 1, then the change of the state will be something like the line in blue. All right, and the eigenvalues in this case, the eigenvalues of A are 0.5 and 1. Keep these questions, and then we will show you the criteria about the stability later. Right? So it seems like it's converging to 1. It's converging to 1, right? But now we have the eigenvalues as 0.1 and 1. They are not negative, right? So which means the criteria for the stability in discrete time systems, they are different. Keep this in mind. I will introduce it a bit later. All right, then let's come back to the standard formulation of the linear discrete time system. So for the linear discrete time system, the standard formulation is xk plus 1 is ax plus bu, and the output y is equal to cx plus du. And all the A, B, C, and D are matrices with proper dimensions corresponding to the x and u. And which means this system can consider multiple dimensions of the state, which means you can hold multiple variables in the state x. All right, and if the initial condition or the initial state x0 is given, and the input is given as well, and you can calculate or you can predict all the xk at any time step, xk and uk in the any time step. This is the same as what we have for the linear continuous time system. But the solution is different. So why we can do that is because we have the solution of it, right? But the solutions for the continuous time system and discrete time system, they are different. So which means we can still do that, but the answers are different. All right. So the x0, I think I remember that I mentioned that in the linear continuous time system as well. So the initial state x0, it can be a naturally starting point, or it can be any starting point that you want to consider as an initial state. Then if it starts at any time, which you want to make it at time step, which you want to make it as initial state, which means at that state, it summarizes all the past history of the system. All right, then the dimension of n in the state, which means the dimension of the state, is called order of the system. It's called the order of the system. And the system is called proper if d is equal to 0. So which means your output is not that's not related to the input, something like that. All right, so that's the general or standard formulation of the linear discrete time system. Then there is your first activity. There is your first activity. Your first activity is about formulating a linear discrete time system for from a real case. All right. So the activity 1 is about student dynamics. It's about student dynamics. So suppose there is a 3 years undergraduate course. There is a 3 years undergraduate course. So the percentage of the students promoted, repeaters, and drop-offs are roughly constant, or you can consider as constant. And direct enrollment in second and third academic year is not allowed. And the students cannot enroll for more than 3 years. So those are the statements. And also I gave the notation already. And let's have a look together. So K is the year, it's the nature year, which means K is 2020, 2021, 2022, something like that. And XIK is the number of students enrolled in the academic year I at year K. So which means I is equal to 1, 2, and 3. So which means suppose X1K means the number of students in year 1 at year 2020, something like that. All right. Then X2K means the number of students in academic year 2 in 2020. And x3k means the number of students in year 3 in 2020, something like that. All right. So in this case, you will have three variables, x1k, x2k, and x3k. All right. And U is the number of freshmen at year k. So which means in 2020 we get UK students and starting in year 1, something like that. All right. And YK is the number of graduates at year k. So which means YK is the number of students graduated from year 3 at 2020. All right. And alpha I is the promotion rate during academic year I. So which means alpha 1 is the promotion rate in academic year 1. And alpha 3 is a promotion rate, it's a graduation rate from year 3. And beta I is the failure rate during year I. And you also have beta 1, 2, 3 as well, right? Those are the notations, and try to formulate this linear discrete time system by yourself. All right. So one point is, after you have your state already, which is x1k, x2k, x3k, and the only thing you need to do is get the relationship between x1k and x1k plus 1, x2k and x2k plus 1, x3k and x3k plus 1, right? Those are the only thing you need to consider. And after you can get that kind of relationship in the formulation or in the equation, then you finish the formulation of the linear discrete time system. All right, so start trying to formulate this linear discrete time system by yourself. All right, so let's look at the this activity 1 together. So as I said, first we need to write the difference equations. So which means I need to find the relationship between x1k plus 1 and xk, x2k plus 1 and x x1 and x2, and x3k plus k plus 1 is equal to a linear equation of the x1, x2, and x3, something like that, right? So if we consider x1 k plus 1, so the number of students, in year 1, in academic year 1 in next year is equal to, there are two parts. Yes, they are. Yes, they are. They are all on the UTS Online. The slides on UTS Online already. All right. So this one I think is in lecture lecture 7. It's in lecture 7. In lecture 8 is linear, is nonlinear. Sorry, the slides on the lecture 8 is the lecture in the next week, something like that. So check it. They are 3. If you find the lectures on the UTS learning material on UTS Online about linear continuous time system, that is, I think, is lecture 6, and after that will be this one, right? So check the title about the what we are talking about in it. All right. So let's go back to activity 1. So the number of students in year 1 in next year, there are two parts. One part is from the refreshment, which is number of new students, which is UK, right? Which is UK. And the other part from the failure students from the academic year 1 in last year. So there are two parts. So which is beta 1 times x1k plus UK, which is equal to x1k plus 1. Then if we think about the number of students in academic year 2 in next year, there are also two parts. One part are the students promoted from year 1, which is alpha 1 times x1k. And the other part are the failures of the students in year 2 in last year. So which is beta 2 times x2. And the x3k plus 1, which is the number of students in year 3 in next year, there are also two parts. One part is the promoted students, from year 2 this year. So which is alpha 2 times x2k. And the other part are the failures in the year 3, which is beta 3 times x3k, right? Then we have the relationships between x1, x2, x3k plus 1 to the x1, x2, x3k, and also the u, right? And the output are the graduates. Graduates means if we have a promotion rate x3 for year 3, then yk is equal to alpha 3 times x3k, right? Then we write all the difference equations already. And the next step is we rewrite it into a matrix format, which is the equations, which are the equations on the bottom, right? So from the first step is we try to write this kind of difference equations. So what's the relationship between the states in the current year, so in the current time step, and the time step in the next right? And then we rewrite those kind of equations into the matrix format. Then we have it. So this is activity 1. And we make a simulation and we show some solutions on it. So for the simulation, we make alpha 1, 2, 3 as 0.6, 86%, 60%, 80%, and 90% respectively. And for beta 1, 2, 3, we have 20%, 15%, and 8%. And if we make the new students for each year constantly equal to 50, and K starts from 2012, then we have the output. We have the output of the system, which are the graduates for each year like this. So this is the input, which is 50, constant for a couple of years. Then for the output from the first couple of years, there's zero graduates, and then after that, there are graduates, and the graduates is converging to constant. Converge to constantly around 40, less than 40, after year comes. So that's the system, and we can see what's the dynamic of the output, right? So that is activity 1. For activity 2, I think this case is a much better case that you can understand and you can practice how to formulate it into the linear discrete time system. And I don't have time to let you to practice on the lecture, but please do practice yourself after the class. All right. So let's go over together. Suppose it's a supply chain problem. Then the statement is the company S purchases a quantity UK of the raw material at each month's K. So here K is about each month, right? And X1 is the material, X1K is the material the S have in month K, right? And after it purchased the UK for each month, a fraction of delta 1 of the raw material is discarded, which means it's thrown away. Then another percentage alpha is shipped into the producer P. This is for each of the months, all right? And for the producer P, a fraction of alpha 2 of the product alpha 2 is sold from P to R, right? And a fraction of delta 2 is discarded, right? And the retailer R returns a fraction of beta 3 back to P every month, and it sells a fraction of gamma 3 to the customer. And then I write all the notations and a figure already here in the bottom. And from this bottom, you can definitely formulate the linear discrete time system. And this is what I did. So again, there are 3 variables. One is X1K, the other is X2K and X3K. It represents the products in the company S, P, and R in the month K respectively, right? So K is the month, which is discrete as well. So then what we want to do is we want to calculate the material in S in the next month, in the K plus 1 month, is equal to what? So it's equal to several parts. First, they purchased a UK in, right, for each of the months, right? And the second is the material in the last month, which is X1K. And also it need to discard a percentage. So which means it will minus delta 1 times X1. And also it will ship some materials to P. Then you need to delete that as well, which is minus alpha 1 times K. Then you have your first equation, right? And for the second one, if you look at this figure, it is quite clear that the products in P, which is X2, in the next month, which is a K plus 1 month, is equal to several steps. The first step is the several terms. The first term is the materials or the products it gets from S to P every month, which is alpha 1 x1, right? And also another part is the returned product from R to P each month, which is beta 3x3, right? And another part is from itself. It has x2k itself. Then it needs to discard a percentage from the x2k. Then you need to minus delta 2 times x2, right? And also you need to shape a percentage from P to R. Then you also need to delete minus alpha 2 times x2. Then you have your second difference equation. And the third difference equation is about the third variable. The third variable. So the products in R, which is x3, in months k plus 1 is equal to first the products from P to R each month, which is alpha 2 times x2, right? And the second part is about itself. So R itself has x3k products, right? And also you need to delete the products returned to x2, which is beta 3x3, right? And also you need to delete the products sold out, so which is minus or delete the gamma 3 times 3, right? So that is the third difference equation. And the y, which is output, are the number of products sold out to the customer, which is gamma 3x3, right? So it is quite clear. So if you can write, if you can draw this kind of figure, and then you have the relationships between the dynamics of the changes of the of each of the state, and then you can write a differential equation. And also another point is if you have three variables, you need to write 3 difference equations. All right. So if you have 3 variables, you try to write each of the difference equation with respect to one variable. All right, and then it's quite easy to formulate it. All right. So I think Malin will also be with you to solve this this example, and also please try yourself to formulate this discrete time system from the example. All right. So this is the definition and also the standard formulation of the linear discrete time system. And as I mentioned before, if you have a linear continuous time system, you can transform it or you can convert it into a discrete time system. If you remember, I mentioned it as a very beginning. So the discrete time system, it can be naturally discrete, or it can be converted from a continuous time system. But if you remember the figure I draw, if we want to convert a continuous time system to a discrete time system, there is approximation, because it is definitely different from what we have for the continuous one, because we only consider the time steps instead of the continuous time, and in each time interval, then the state value is constant, right? If you remember that. So which means the discretization, we have the ways to convert a continuous time system into the discrete time system. But the thing is, the discretization methods, they are approximation. They are not exact, they are approximation. All right. So there are two ways to do this discretization. One way is called the Euler's method. The Euler's method is derived from the definition of the derivative. It's from the definition of the derivative. All right. So if you look at the equation here, so suppose we have this differential equation. So this standard formulation of the continuous time system, which is x dot is equal to ax plus bu. And we want to convert it into this kind of discrete time system, which is xk plus 1 is ax plus bu. Right? So how we can do? So the first thing is we need to change t into kts. So ts is constant, is the time interval. The time interval is ts, and k is the time step. So first we need to choose the time interval, which is ts, and convert the time t, small t, into kts. And then sometimes you can delete the ts in the variable, something like that. All right. So that's the first step. And the second step is the Euler's method. So which is it starts from the definition of the derivative. If you look at the equation here, so what we want to do is if we can replace x dot by using xk and xk plus 1, then we can somehow convert the equation into the discrete time system, right? So we need to replace x dot, so because there's no x dot in the discrete time system, and we want it still have xk and xk plus 1. And what we can do for Euler's method is for the definition of the derivative. So the derivative of x with respect to time, which is x dot, is equal to limit the ts is coming to 0, the limit towards to 0, and xk plus 1 minus xk divided by ts. So the definition of the derivative is the difference or the changes of the state divided by the interval, which is ts, and limit this interval ts towards 0, right? But here we can't make the limit, so we make approximation. So which means x dot is approximately equal to xk plus 1 minus xk divided by ts. Then you have x dot, right? So you replace x dot here by using this. You replace this x dot here by using this. Then your equation only have xk plus 1, and bk, right? And then you can rewrite it into the standard formulation of the linear discrete time system, right? So that is Euler's method. The Euler's method comes from here, comes from the definition of the derivative. And then after you know about this approximation, you back substitute this equation to the x dot, and then in the equation you only have xk plus 1, xk, and uk. Then you can rewrite it to the standard formulation. All right, so that's the Euler's method. Another method is called the Tusting's method. So Tusting's method is another way around. So which means the Tusting's method comes from the integration instead of a derivative. All right. So the difference, so the changes between xk plus 1 and xk is equal to if we have the derivative of x with respect to t, and we do the integration of this x dot from k to k plus 1. And because we know x dot is equal to ax plus bu, And then we can replace x dot by using this. Then this is a trapezoidal rule. So if we want to integrate this function from k to k plus 1, it is equal to half of the time interval, half of the area that the distance that you integrated, which is ts divided by 2, and times this equation evaluated at here at k, and this equation evaluated as at k plus 1. Then we have this. So which means xk plus 1 minus xk is equal to this. That is from the trapezoidal rule. And you can see in this equation, you only have xk, xk plus 1, and uk. Then you can rewrite it into the standard format, standard formulation of the linear discrete time system. Then you have it. All right. So there are two ways. There are two ways to do the discretization, which means there are two methods that you can convert the linear time system to a linear continuous time system to the linear discrete time system. But from the two results, you can see the discrete time systems got it converted by using the two different methods. The results are different, so the systems are different, right? So the converted discrete time systems are different by using two different methods. Why is that? Why is that? It is because, as I mentioned, it's approximation. If you want to convert the continuous time, which is smooth continuous time system, into discrete time system, there must be an approximation. There must be an approximation. And for different methods, for the Euler's method and for the Tusting's method, the approximations are different. So that's why the resulting discrete time system, they are different. All right, so that is the discretization. And another one is the stability. So we introduced the stability already in the continuous time system. So the stability is that, this stability is for the continuous time. So I copied that to here to make you recall. So if you have a linear continuous time system, that system is called asymptotically stable if for any initial state, the state xt will converge to 0 as t increase indefinitely. So which means in the continuous time system, if the state will converge to 0 when the time increase, then that system is stable, right? And we gave some examples on that already. So we have the criteria. So the condition of the stability is for the continuous time system is all the eigenvalues of A have negative real parts, or negative or have negative real parts. So which means the stability of the continuous time system only depends on the matrix A first. And if you want to check the stability, the next step is to calculate all the eigenvalues of the matrix A. And if all the eigenvalues of matrix A are negative or have negative real parts, then which means the continuous system is stable. All right, so if A is a 3 by 3 matrix and there are three eigenvalues of it, and the first eigenvalue is -2, the second eigenvalue is -3, and third eigenvalue is 1. Then in this case, the system is not stable because it is stable only if all the eigenvalues are negative or have negative real parts. All right, so this is for the continuous time system. But for the discrete time system, I will show you which is a little bit different. So if we consider a very simple case, a very simple first order, so there is only one variable in this case, then xk plus 1 is ax plus bu. Then if we choose u equal to 0, which means the input is equal to 0, then the solution of that case is xk equal to a power k x0. Then if we gave the initial x0 equal to 1, then if a is larger than 1, you get the state changes as the right line, right? And which means it start 1 is getting larger, larger, and larger. It's quite easy, right? If A is larger than 1, it's getting larger and larger. Then which means this is not stable, right? This is not stable. But if we choose A equal to 1, then it will be constantly equal to 1. But if we choose A between 0 and 1, because it's A powered k, if we choose A between 0 and 1, you can get the line in the purple. So which means in this case, it converges towards 0, right? Right. So as you can see here, the quaternions for the stability in the linear discrete time system is a bit different from what it has in the continuous time system. Then what are they? What are they? So the definition of the stability is exactly the same. So if the system is stable, then the state x will converge to the 0 when the time step increases. So the definition is exactly the same. But how to check the stability of the discrete time system? What are the quaternions? And the second thing, which is the same to the continuous time system, is that the stability also only depends on the matrix A. The stability only depends on the matrix A as well. All right, and the quaternions are different. The quaternions are different. So so the quaternions for the continuous time system is if all the eigenvalues are negative or have negative real parts. But here the criteria is that if all the eigenvalues of A are between 0 and 1. So which means if the absolute value, so for all the eigenvalues, if the absolute value of the eigenvalues are less than 1, then that is stable, right? So if any of the eigenvalue, the absolute value is larger than 1, which means if any of the eigenvalue are larger than 1 or smaller than -1, then which means the system is not stable. All right, it's not stable. So that's the stability. It's a bit different. It is a bit different. So so let's look at activity 4. Then I don't think I have time to let you do it during the class, but you can definitely practice on it later. So suppose we have this. Linear discrete time system. Then there are two questions. One is what's the solution? The other is what's the stability? And let's look at together. So for the solution, again, the solution, you don't have to write it like that. You just need to replace the matrix A and B to the equation by using the real one, and that's it. You don't have to do the calculation inside the matrix. Again, you don't have to do the calculation inside the matrix if there's a question in quiz 2 or in the final exam. All right. So this is solution because it's quite because this one is a bit special. Then we can calculate inside, but you don't have to in the real case. Sorry, in the exam or quiz 2. So this is the solution, and we can write. We can draw the figure about changes of the state as well. Then for the eigenvalues of A, so we calculate 2. There are 2 eigenvalues of A. One is 0, the other is 0.5. Then both of the eigenvalues are between -1 and 1, which means it is stable. It is asymptotically stable, and it is stable, right? So this is activity 4. Then we change a little bit on the activity 5 on the matrix A. Then what is the solution? The solution, again, you don't have to write it like this. You don't have to write it like this. You just replace A and B into the solution equation, and then that's it, right? And that's the solution, and also the stability. The eigenvalues of A, there are 2. One is 0, the other is 2, right? So in this case, I have one eigenvalue which is larger than 1. then which means it is not stable, right? And we can also draw the solution to the figure, then we can see the state will change larger and larger. It's not converging to zero, right? Then which means it is not stable as well. Okay, so try to practice on activity 4 and 5 by yourself to see if you can properly get the solution of the linear discrete time system, and also check the stability of it. All right, then this is a summary about the stability conditions for both continuous time system and discrete time system. And the similar things are, first, it only depends on the matrix A. And the second thing is, it depends on the eigenvalues of A. Right? Those two things are exactly the same, but the criteria are different. For the continuous time system, if all the eigenvalues are negative or have negative real part, then which means it is stable. Otherwise, it's not. But for discrete time system, if all the eigenvalues, the absolute values are smaller than 1, so which means if all the eigenvalues are between -1 and 1, then that is stable. Otherwise, this is not. All right. So why I'm listing here is because the criteria is a bit different. And if you have a question about examining the stability of the system, the very first thing is you need to first identify if it is a discrete time system or a continuous time system. They are totally different. All right, so if that is discrete time system, then you use the criteria for the discrete time system. All right, so that's the stability. Then the next thing is the controllability. Again, so if you have a linear discrete time system, then you want to do the pole placement, or you check the stability. It is not stable. Then you want to do the state feedback control. You want to use the pole placement or Optimum control to make it stable. But the thing is, at the beginning, you need to check the controllability, if the system can be controlled or not. Right? So that's the controllability. And for the controllability to the discrete time system, the criteria, everything is exactly the same. It's exactly the same as what we have in the continuous time system. The stability, the criteria are different, but for the controllability, they're exactly the same. So you need to first calculate the controllability matrix, which only comes from B and A, right? So that is exactly the same. And if this controllability matrix is 4 rank, then which means that is controllable, right? So that is the controllability. To check the controllability, everything is exactly the same in both the linear continuous time system and discrete time system. All right, so that's the controllability. And here's your activity 6. I don't have time to do it during the course, but try to practice on yourself. So for this system, if the system is controllable or not, the first thing is you need to calculate the controllability matrix. The first column is B, which is 1, 1, right? The second column is A times B, then which is 1, 1 as well. So it is not 4 rank, right? Because the first column is the same as the second column. It is not 4 rank, then which means it is not controllable, right? And also, if you calculate the determinant, is 1 minus 1, which is 0, then which is not 4 rank, which means it is not controllable. All right. Then for pole placement, the idea is exactly the same. So you use the state feedback control, so which means your control U is equal to minus kx. So use the state as the feedback to control. So that is state feedback control, which means U is equal to minus kx. And in this case, the new closed loop system becomes A minus bkx, right? And your new A matrix is A minus bk. And the thing you need to do is you choose a proper k to make this new A minus bk, all the eigenvalues are between -1 and 1. All right, so the process is exactly the same, but the criteria is different because in this case, it is this linear discrete time system, and the stability criteria is different. All right, so the process is exactly the same. Is U is equal to minus kx, and then you choose proper k to make the new A matrix, which is A minus bk, has all the eigenvalues between minus 1 and 1. And then you can make your system stable, right? So that is pole placement for linear discrete time system. The process is exactly the same as what we have in the continuous time system, but the criteria about stability is different. All right, so try to remember about that. Then after that, we still have this optimal control. So for pole placement, we can have multiple Ks, right? But which K is optimal one? Which K is the optimal one? Then we have the optimal control. But in the linear continuous time, let's recall for the optimal control in the linear continuous time system. So the optimal control is about to get an optimal K, right? And how we can do it is we solve the Riccati equation. We solve the Riccati equation listed here. We solve the Riccati equation listed here to get P, matrix P. And from matrix P, we can get the K. That is the optimal K. And from K and P, we can get the U. And we can also calculate the minimum performance index, right? So this is the optimal control process for the linear continuous time system to get an optimal K, right? So for the discrete time system, the idea and the process are exactly the same, but with some differences on the equations. So the idea and the process are exactly the same comparing to the linear continuous time system, but some equations are different. So let's see together. So for a linear discrete time system, so we want to do the optimum control. And the first thing is we design the state feedback control. We still use the state feedback control, so which means U is equal to minus kx. We still use that. And we want to choose the optimal K. We want to choose the optimal K, which minimize the performance index. So the performance index for the linear discrete time system is different from the linear continuous time system, if you can compare. So the performance index, we still want to get optimal K to minimize the performance index. But the performance index itself, the equation is a little bit different comparing to the linear continuous time system. All right. Then how to solve it is we still solve a Riccati equation to get P. And from P, we can get K and U. But the equations are a little bit different. So please still remember. So how to solve the optimum control is the process is the same. First, we calculate the P from the Riccati equation, but the Riccati equation is different. The Riccati equation is different from what we have. And the next step is, after we get P, we can get the matrix K. And again, this equation is different from what we have in the continuous time system, right? From P, we can get K, and from K, we can get U. All right, so that's the optimal control for the linear discrete time system. All right, so this is all for today's lecture. And in the next lecture, we will introduce the last part of the control, which is nonlinear discrete time system. It's still a discrete time system, but the system is nonlinear, which is different from what we have in the linear continuous or linear discrete time system. It's a bit complicated. All right, so that is all for today. And so in quiz 2, we will contain everything after quiz 1 and until now. All right, so that's the content. It can be in quiz 2. So any questions on quiz 2? If you still have any questions on quiz 2, then you can ask now. You can unmute yourself and ask now. Any questions? Any questions? Okay, so if there's no questions on quiz 2, again, the quiz 2 will take at the beginning in the next lecture. It will be 15% of the marks. Then it will take 40 minutes. You will have 5 minutes at the beginning to download and read the question paper. And after that, you can make your report or answer of quiz 2 on the Word document, or you can handwritten it and take a picture to submit. All right, and it is not restrict open book anymore. It's totally open book. You can check any of the materials, and also you can use MATLAB as well to do some calculation, but don't copy the code from the MATLAB. I want it as a solution of a question, of a proper question. All right, even you use MATLAB to do the calculation, you need to write down the process about solving the question. Also, you need to write down each of the steps and also the equations you have. All right, so you can only use the MATLAB to calculate numbers, but I don't want to see the code from MATLAB. All right, so if all good, let's move to Malin to have the hand-on activities. Thank you very much.